codes now and answer a few questions basically. The code that I'll be taking from, let me first show, this is not something that I have written myself. So what you can do is, let me share my screen and show this. As discussed last day, that you can go to this quantum.cloud.ibm.com, sign in if you want, but you don't need to for this. Go to this tutorials. Here you will find so many tutorials for many kind of things. As you can see that these are kind of the very recent kind of stuffs. These are very updated and recent stuffs. These are kind of VQE, perhaps you have heard of these things, machine learning, um, new tricks, how you can optimize your circuit better, all of those things. But if you go to fault tolerant algorithms, you will see this Grover's algorithm is here. And this is the thing that I'll follow precisely. So whatever codes that I'll show you, you can just go, and this is downloadable notebook. You can just go and download, and this is open to all. Um, so let's go to the code now. But before going to this, you can ask this question, and you should ask this question basically, that if Grover's algorithm has this speed up, we have seen the speed up, maybe we haven't been too rigorously mathematical, but at least I hope that intuitively we have understood that it has a mathematical rigorous proof that it can give you quadratic speed up. So why don't we use this Grover's algorithm? It is not perfect. Of course, it is not perfect. I mean, it's not polynomial time. If this were polynomial time, then you could have showed that P is equal to NP in quantum, which is not true. Um, at least which has not been proved or disproved. So which is not true is a very strong word. It has not been proved or disproved. But at least there is a quadratic speed up. That actually is very good. That's not, I mean, that's not perfect, but that's actually very good. So the question that you should be asking definitely is that why don't then we just use this method to solve this combinatorial optimization problems? We could have done that, and that will give us a significant speed up over whatever is done now. And we will look into the code, and we will actually see the reason why it is still not the case. Wait. Sorry. Okay, there is one question. How do we know the oracle has correctly picked the mark state? Yeah, so see, whenever we come to this oracular problems, we don't really question the oracle. Even before you have done, say, Simon's algorithm, where I hope you have done Simon's algorithm, there is a secret string. You have definitely done Deutsch-Jossa algorithm, where there is a promise that the function is either balanced or, I think, constant. So we don't really question the oracle here, because if we question the oracle even in Deutsch-Jossa, say, and we say that, okay, what is the guarantee that the function is balanced or constant? What if the function is something else? Then your entire algorithm breaks down. So we assume that the oracle is prepared properly, and the oracle is correctly picking the mark state always. So it is able to put the phase on the correct mark state always. Again, intuitively speaking, it how is the oracle implemented? We are going to that oracle implementation right now. So this is the same notebook, as you can see, that I have downloaded from here. This is the Grover oracle. This is the Grover oracle. So you see what it takes. It takes the mark states here, takes the mark states, and it the oracle itself is a quantum circuit for our case. So it is creating a quantum circuit. The number of qubits is like from there. Now what it does is Now what it is doing is that whenever there is, so let's say that the mark state is say 0, 1, 1. So whenever there is a zero index, you apply an X gate there, and then you do an MC empty. If you're not clear what is MCMT, I'm coming to that. So it is multi-controlled multi-Toffoli gate. So it's basically a multi-control Toffoli gate. So it's like a C naught. C naught is one control, one target. This can be, say, there are two controls and one target. So if it is a 3-qubit system, think of it like if both qubit 1 and qubit 2 are 0, then qubit 3 is flipped. Then it's a two controlled, one target. So this is the general thing, that it can be a multi-controlled multi-target. And the control comes from that what are the actual, if there is a 1 or not. That's how the control goes, and you flip accordingly using a, and then you apply a Z gate here. So that's kind of the phase that is applied, right? So you do a multi-control Toffoli, you don't really do a C naught here, you put a CZ here. So if the control is 1, then the target's phase is flipped. So here it's multi-control. So that means if there are, say, two controls, both of the qubits above are 1, then the phase of this qubit gets changed. And then again, there is, you look into all the zero indices and you put an X gate. So this is the way of building up the oracle here. But in general, think of it, I mean, this is something we often get a bit confused. Yeah, I mean, it's not wrong to get confused. Even I used to feel uneasy that, okay, you already know how to build the oracle. You are building the oracle yourself. Then why do you need this Grover's algorithm? If you already know everything in the oracle, then you could have just used the oracle to find out the original mark state, right? That's not, in general, that's not how the oracular algorithms work. Oracle algorithm is not only for quantum. There are many classical algorithms which are also oracle algorithms. So the oracle algorithm assumes that, say, I have built the oracle, you are allowed to use it, and you can solve your problem using this. So we will actually see this happening here. So we run this here. I'll do two things. I'll run it on a simulator and I'll come back to this. The example that I have taken, it's actually a 4-bit. I think in the tutorial you will find it to be 3 bits. I think I took 5 bits. There are 2 mark states. So as we discussed, there can be more than 1 mark states. There are 2 mark states. And I prepared the Grover oracle. This is what the oracle looks like. So as you can see that the Z gate is applied here, and wherever there are zeros, the X gate, wait, sorry. Okay. Sure. Increasing the font. Thanks. I hope this is good now. Okay. So now if we look at the Grover operator, this is what the Grover operator looks like. So as you can see, this is what the Grover operator, wait, let me minimize this. Yes, now I can see. This is my oracle. This is what my oracle is. What do I do? I put my oracle and then equal superposition states and everything. This is what my Grover operator, which is the inverse, which is the phase followed by rotation together. Now, how many times do I need to do the number of iterations? See, that was given by pi by 4 times square root of n. This is what we do, and we find that we need to do 3 iterations of Grover operation here. So my full Grover circuit, I prepare it in the equal superposition state. Then I take this Grover operator, which is doing the negative phase followed by the rotation, however you look, and I am repeating that. Sorry, where did it go? Yeah, I am repeating that 3 times. This is what you can expect to see. You don't know what is going on here. These are the Grover operators. These are kind of black boxes. This is how you should be like visualizing the thing. Okay, I don't understand this question. How is the unstructured data or database input? Oh, okay, I see. Yeah, the database inputs are always zeros and ones. The database inputs, because even if you are not solving a graph problem or a combinatorial optimization problem, even then, say out of 5 elements, you are looking for the first element. That is your mark state. Then you can say that it is 1 0 0 0 0, something like that. So it is always like the database inputs are always looking like this. And this is what you should be thinking that the oracle looks like to someone from outside. The someone who is using the oracle doesn't really have access to this entire circuit. They don't know what is going on internally. This is how we should ideally have, that someone else prepared the oracle, I am going to use it. Now what we need to do is I need to step 2 for, so I have prepared the circuit. This is a very small 5 qubit case. I mean, you can very easily solve it in a classical computer. What's the even if it's a combinatorial optimization problem and you have say 5 nodes or something in a graph, it's very easy to solve in a classical computer. But we are going to take that as an example here. So next step that I need to do is to see a quantum computer doesn't understand these. A quantum computer has some basis gate sets. We can actually draw the quantum computer here. So from Qiskit dot visualization board. So this is what my quantum computer looks like, right? So you can see that the quantum computer has some coupling maps and everything. But more importantly here is that if you look into this, perhaps you know about this, but sorry if this is just a repetition. So these are the basis gates. What are the basis gates? If just like in classical case, if you can build AND gate, OR gate, NOT gate, you can put everything together. I mean, for any logic, you can actually implement that using those three, or even you don't need both AND or. If you have NOT, you can have any one of AND or OR. Similarly, a quantum computer understands these gates. Whatever unitary that you prepare, this is definitely a unitary. Whatever unitary you prepare, you have to break it down into the basis gate set. And your circuit should not look like this to a quantum computer. It should be built using these gate sets. And this is done by something called transpilation. For transpilation, we do this generate preset pass manager. We pass in the target, which is kind of the backend dot target, and optimization level 3, because if 1000 names have to be searched, you need some binary encoding of that name. You need some binary encoding of that name. Just like in machine learning, when you have a data, you can do those one hot encoding or better encoding schemes. You need those kind of encodings if you have the 1000 names. So optimization levels, this is actually a hard problem. This is shown to be an NP hard problem, this mapping of a quantum circuit to the underlying hardware. And we do, so it's a basically heuristic, and how much time that heuristic will take, that can be dictated by doing the optimization level. If you do optimization level 1, it does a very light heuristic which may not give you a very optimal solution. Optimization level 3 is the best out of this. So I am doing this transpilation, and this circuit is called circuit ISA, which is instruction set architecture. So this circuit conforms to the instruction sets here. This circuit will only contain these instructions, nothing more. Transpilation does something more, but that is not really required for us at this point. But what I want to point out here, this was my circuit, right? It looked so nice, simple. Let's look into the circuit that will get executed on the hardware. Wow. Okay. So this is the circuit that will get executed on the hardware. You can understand how big this is. This is again just for 5 qubits, but you can understand how deep this is. Why is it so deep? Simple. It's because you see all these are single qubit gates, rotation around Z, Sx, so that's square root of X gate, this is identity. Cz is a 2 qubit gate. Here we have 5 qubit gates. And when you break down these 5 qubit gates, what does these gates actually look like? They consist of this multi-controlled Toffoli, MCMT, right? And the moment you break it down, the decomposition of this multi-controlled Toffoli is extremely costly in terms of the number of gates. So that is from where this circuit is coming from, which I keep on scrolling and scrolling and scrolling. But this is the circuit which now gets executed on a quantum computer, not some very small, nice looking circuit. Okay, cool, no problem. So now we are creating our sampler. We want the probability distribution. The distribution, the output states will give me the mark states, which should be the correct solutions. So I have created two cases. One is a simulator, an air simulator. There is no noise here. And one where I have taken a fake backend, which has noise. It's the fake Torino. It's the coupling map that I was showing you. So we have created two samplers. I'll just run this. This is the ideal result. And this is the backend result. That is what happens when there is noise in the backend and everything. So let's look into the ideal result first. Fine. These are the states that I was looking for. This state and this state. These were my mark states. And you can see that I am getting this with probability, say 0.95, around 0.95 or something, which is very nice, right? Yeah, I think, yeah, if we add this, it will be around point, I think it's exactly 0.96 or something like that. So that's very good that with 96% probability, I'll get the correct outcome. Each of these, we already discussed that if there are more than one mark states, the probabilities get equally distributed. So roughly 50%. How is the probability of the mark state measured after each iteration? It is not measured after each iteration. If you see that we had 3 iterations, we determined before that by doing that calculation that it needs to be pi by 4 times. Sorry, where was that calculation? Yeah, we saw that it needs to be 3 iterations. This was the circuit. It was not measured after each iteration. We had 3 iterations of this. Then we finally measured the circuit. So we need to first find out what is the number of iterations. Only then we can build the circuit, not otherwise. But we see the outcome, that the outcome is good. It's around 96% probability that we'll get the correct outcome, which is very nice for a probabilistic algorithm. And the probability is roughly equally distributed between the two mark states, right? Let's look into the noisy solution. This, remember, this case here, I had run it on a noisy backend. You see the probability of getting a correct outcome is roughly 0.12. This and this added. So we ideally calculated that how many number of iterations should there be. We found out that it should be 3. You can ask a question that, okay, you understand this is coming because of noise. You can ask that, should I increase the number of iterations? No, we already discussed before that if you increase the number of iterations, the probability of getting correct outcome will actually reduce now. And then it will start increase sometimes later on. But you cannot increase the number of iterations. You have already found the optimal number of iterations here. And when you run it on a noisy fake backend, it is giving me, yeah, okay, coming to this question. So it is giving me that I am getting the correct answer with probability 0.1. And remember, this is for a 5 qubit case. So it is kind of a graph with 5 vertices, which we can solve very easily using a classical computer. Um, so, so this is what we get here, and you can understand at this point why we don't use Grover's algorithm at this point. So all the algorithms that are mostly going to be covered in this QT, I'm sure there will be more near-term algorithms in later QTs and everything, later courses. Here, what we see is that um, these algorithms are not good enough to be executed on current quantum devices. Current quantum devices don't have error correction or fault tolerance. There is noise which you cannot account for. And even without going to a hardware, what we see here is this. So there is a question, what does it mean by hardware circuit? What it means here is that I have mimicked the effect of a hardware. I have mimicked the effect means I have broken things down into the basis gates which the hardware recognizes, and I have incorporated a model of the noise, not the exact noise. The hardware has many noise which cannot be very efficiently modeled mathematically. I have made an approximate model of the noise of the hardware, and for such a small problem, we end up seeing that we are not really getting anything, like 0.1 probability. What does it do? It doesn't do anything, right? This is kind of a reason why Grover's algorithm, Shor algorithm, all these algorithms are not applicable in near term. They are definitely very, very useful algorithms which will become applicable once fault tolerance comes in 2029 or something. But at this point, these are not. And this is the reason why this kind of Grover's algorithm is not used in the industry today to solve all these NP hard problems. Because, I mean, see, this is what is happening on 5 qubits. Okay, so there was a question, is the number of iterations 3 because n equal to 9? No, n was equal to 5. But remember, root 5 is roughly 2 point something, and there is a pi by 4 multiplicative factor of that. So, and then we take the floor of that. So that's where it is giving n equal to 3. Number of iterations equal to 3. So this is kind of the reason why currently it is not useful in industry at least, but these are very, very important algorithms that you should be learning. At the same time, you should remember that if you are going to work on quantum computing today, these are not the algorithms to opt for. These are the algorithms which are beyond 2029 or something, and you will, I'm sure you will look into these things in later courses, that there are already tons of brilliant algorithms that we are kind of finding and doing useful works there. Okay, so there is a question, if we already know the mark state, then what are we searching in the database? Not really the case, right? See, the oracle can identify the mark state. All the calculations that we did is how the system is evolving, that there is an orthogonal things and everything. This is not really something that you or I get to see in reality. Those orthogonal things, this is W, this is psi other. We don't see these things, right? We are just searching for, say, that's why this database search is a bit confusing thing. This is why I don't really like to stick to this point of database search. Think of a SAT kind of problem, a graph problem whose solution you are trying to find. You don't know the solution. Of course, if you knew the solution, then what are you searching for? True, very, very valid question. But what we can do is, there are exponentially many candidates. We can prepare an equal superposition of those exponentially many candidates. We assume that the oracle is able to identify the valid solution correctly. How it can do that? That's up to the oracle. Here we saw how to do that by doing ourselves, by building the oracle ourselves, but that's not how it's supposed to happen. And theoretically speaking, it means that it is easier to verify that a solution is valid for NP complete problems than to find the solution. So we prepare the equal superposition of all exponentially many candidates, and then we give it to the oracle. Oracle will do these flips and everything, do the number of iterations, and we will get the valid solution. When we measure the quantum circuit, we'll get the valid solution with very, very high probability. And there was one question. Yes, so if you go to the IBM quantum device, sorry, let me then share my screen once more to this. Wait, wow, what happened? Okay, I don't know what is going on here. I hope this is visible. So if you go to this quantum.cloud.com, this thing, you will see there are a few things. Here is a composer. If this is what you were asking for, this composer is definitely free, but you can only do very small stuffs here. This is good if you are just getting started. Say, yeah, I put in a Hadamard, I put in a C naught, and you see how the probability changes and everything. So this is very good if you are just getting started, and you can also see you can get the corresponding Qiskit code here, but this is not really scalable, right? I mean, you want to take your problems to those regimes which are not solvable classically. Otherwise, what is the point of even using quantum? I mean, that's kind of the reason I showed you what is the current drawback of Grover's algorithm. It's awesome, it's great, it's mathematically rich and everything, but you cannot use it today to solve actual problems of interest. So unless you are thriving for that, then it doesn't make any sense to say that, okay, I have solved a 3 qubit problem. You could have just done that using a classical computer also. So this is very good to get started, but it's ideally better that you download Qiskit and you start learning it, you writing your own codes. Also, when you go to this IBM Quantum platform, and you can get 10 minutes of free access every month. 10 minutes is a lot because each circuit takes less than a second, even sometimes in milliseconds, depending on the size of the circuit that you are running. So 10 minutes is actually a lot to get started with. Okay, I hope that answers your question. Yeah, so that's all I wanted to talk about. If there are any more questions, we can discuss. Okay, if not, um, should we stop here? In the, okay, there is one question. In the NIST quantum computers, are we saying VQE, QAOA, and other optimization algorithms are the ones being used even though we have noise? Yes, there are definitely some candidates which are being used, which are can show good performance even in the presence of noise, but they are not the only algorithms. These are the variational algorithms that you are talking of, VQE, QAOA. There are many other types of recent developments. All of these are shown to be pretty good and pretty, and that means really, really good even in the presence of noise. Deutsch-Jossa, Shor, Grover. So Deutsch-Jossa is more or less a toy problem. There is no immediate application of that. It is kind of a toy problem which shows that quantum can be exponentially powerful over classical. There is no immediate application why you want to distinguish between a function which is constant or balanced. Shor algorithm, the application is very well known, like it's factorization, right? In prime factorization. So the day we can actually do Shor algorithm very efficiently, we can break the we can break all these RSA crypto systems and everything. But in general, prime factorization gets an exponential speed up when we do Shor algorithm. And Grover's algorithm, basically, don't think of it as a database search, although Grover's original paper called it a database search. Think of it as a tool to quadratically, or not a tool, think of it as a method to quadratically speed up the problems, the combinatorial optimization problems. I haven't used Qniverse, but I heard that you can run the same Qiskit code there. And okay, they enlighten on how QC can be used on security. So yes, I am not really an expert in security, but there are many protocols where you can actually show that you can provide a much better security, or in some sense, one of the things you know is the no cloning theorem, and the other one is um, more or less the I know of. There are many protocols. There is one thing is no cloning theorem. That means you cannot really get hold of my state and copy it. The other important thing is that many of the protocols show that if you do some tampering with my state, even though you cannot copy it, but you try to tamper with my state, you will get detected. And in classical, you can often remain undetected but still tamper with the state. So I mean, again, I'm sure anyone who is actually an expert in security will be able to give you a much better detail on this. There are definitely some implementations of security and communication. um, there is a very good startup called QNew who are working a lot on these things. And as you perhaps know that on NQM, IIT Madras is the hub of quantum communication, and they have actually showed practically QKD and something. Even I think a month or something back, IIT Delhi actually showed this QKD kind of things, all of those things. Yes, these are implementable, but they still needs to get into larger scales. Um, why IBM is focusing on software or coding based quantum computing in India, not hardware based. So this is something that I guess the top leaders of IBM can actually answer. Uh, I am a very junior employee here. I am not the correct person to answer this. But I think IBM is a US institute. These things got started in US and they are already way ahead. So they are continuing there. You said there are billions of no, no, I'm sure there are not billions of algorithms. I'm sure there are many algorithms. People are proposing specific algorithms for specific problems. Yes, this is kind of true that there is perhaps nothing like saying that one algorithm solves every problem. This is not even true in classical domain, right? That we have specific algorithms for specific problems. But there are kind of certain types of algorithms. Say if you want to solve a machine learning problem, there are a family of algorithms which actually suits the machine learning problems. There are kind of chemistry kind of things that actually suits chemistry kind of problems. So that is definitely there. So there is one more question. Can we use quantum ML for stock market prediction in fintech domain? I'm sure you can, but again, at the same time, as far as I know, there is no proof that quantum ML is doing any better than classical ML in this kind of things. That doesn't mean that we should not stop pursuing. I mean, we should stop pursuing those directions. We should actually be trying hard and try to find out where quantum can actually beat classical. Okay, so if there are no more questions, I guess why are the application experts? Why all application experts move to QC? Ask the application experts for this. HPC is not good enough. No, HPC is definitely not good enough, and this you can easily show. This you can easily show. See the type of thing that I showed today, the way Grover algorithm works. Can you do that using an HPC? Can you actually apply a phase on a bit, you can say that, okay, you are creating an equal superposition of 2 to the power n states. I'll create kind of 2 to the power n threads and I'll run those parallelly. Can you create the phase there? Can you do this kind of inversion there? You cannot. So there are problems which are not really um, classical, and if they are not classical, that means HPC is not good enough. Of course, it's like so what is it hyper or not for our applications? Sure, there are definitely applications where HPC are good enough, definitely. But HPC is not kind of a replacement of quantum. Saying that I have more powerful HPC is not the answer to go against quantum. And coming to one and actually connecting one more question to that, how can quantum computing be used for finding new molecules or materials? There has been some recent developments. If you see, there's something called sample-based quantum diagonalization. What it shows is that instead of trying to say that quantum is better or someone saying HPC is better, we should be tying hands together. There are stuffs in which quantum is better. There are stuffs in which HPC is better. Quantum is not here to replace HPC. HPC cannot replace quantum. And if you tie them together, you should look into this sample-based quantum diagonalization thing. If you tie them together properly, what it shows is that you can actually do problems way faster than what quantum alone can do, what classical HPC alone can do. So please do look into that algorithm. Again, I haven't done cancer detection image processing, but I hope it is possible. Just look into one small thing that often when you go for image processing, what I have seen, I'm not an expert here, so don't take my words as the final words. But what I have seen at that these image processing circuits become very, very deep, and eventually you end up processing images much, much smaller than what you could have done using a classical computer or an HPC. So instead of naively trying to replace existing ML algorithms using quantum, it is better if you kind of think that what are the cases where ML is failing. So this question that was asked, that is HPC not good enough? This is actually a valid question. You should be asking where HPC is not good enough. It doesn't make sense to say that, okay, HPC is doing great, but I'll still do quantum here and then I won't be able to match up to HPC. What's the point of that? So it's better to try to find scenarios. Image processing can definitely be one of them, but one of the main constraint to that is the depth of the circuit that is happening nowadays. If you can find a way, better algorithmic way to come up with lower depth circuit and show that something quantum is able to do that classical is not doing, great. Grading and scoring, I'm not sure I follow this. Grading and scoring of what? Okay, this is an interesting question. Can you suggest some new emerging areas where QC is going to be used in near future? There is no one correct answer to this. So whatever I say here, don't think like that these are the only areas that can benefit from quantum, nothing else can. But from the perspective of IBM, there are 4 working groups, and these 4 working groups correspond to the things that we expect will bring quantum advantage, that these are the domains where quantum is going to be um, better than classical things. One of this them is material science, chemistry problems. One of them is high energy physics. One of them is life science and bio, so drug discovery, biomolecules, and everything. The fourth one is optimization. These are kind of the 4 uh, areas where we feel that quantum is going to give some promising results, maybe advantage over classical sometimes very soon. That doesn't mean that other domains are cannot give any advantage. Again, I am not the right person to answer about quantum random number generation. I don't work in these communication of or security. Okay. So here is a question: is algorithms like quantum parallelism, Deutsch-Jossa have any application in QML? Not directly, but the way it works, I learned it very little. I am not an expert. I learned it very little from one of the faculties in ISI. There is this idea of learning theory, which is kind of the theory of machine learning. See, machine learning is kind of saying that I have a function. You don't know about the function. You are trying to, it's a oracular setting if you think that I have a function that kind of classifies cat and dog images. If you knew the function, you would have solved it. But since you don't know the function, you are giving some training case. That's what is the training about? You are trying to come up with a hypothesis class, which is a very good approximation of the function f. This is what the training is, right? And you can actually show that these problems like Deutsch, Jossa, and others, there are many functions which you can learn better using quantum, that is with fewer queries. This is something where QML can be very advantageous. QML requires fewer queries than classical ML, which means, and there has been many reportings of this also, that when data is less available, that is the region, the domain where QML is starting to show some benefits over classical ML. The learning is better in the presence of fewer data. PQC, sorry, again, not a security problem. Uh, to solve large problems on HPC, it's the algorithm that drives. If you got the way the Grover's algorithm works, it it is not something that you can do in HPC. Quantum is not like trying out parallel things together. If quantum were just that, then you could have just mimicked it properly with an HPC. It's the algorithm and the way it works, interference, superposition, entanglement. These are the things that drives the quantum system that is not possible in HPC. Okay, so I guess we are more or less done. So these are all things that are worked on, right? That compute, memory, IO, communication, everything is being taken care of in quantum also. Right now, when I talk of this SQD, which is kind of something that is called that quantum centric supercomputing, then it's there is a lot of study going on. I can at least tell you this much, that there is an entire dedicated group in IBM that take cares of what you have written: compute, memory, IO, communication. These are taken on very seriously for these things. Otherwise, such a scalable 156 qubit quantum computer wouldn't have been possible. Um, aren't we programmatically telling the oracle to mark the? Yes, yes, this is true. So there is one question, I think it's privately, that aren't we programmatically telling the oracle to mark the quantum states? This is true. The way we did here, the way I showed the code, this is absolutely true what you have written. But whenever we talk of oracular algorithms, even in classical, we assume that the oracle somehow exists. And the problem that I know many of you are thinking of, that is actually valid, that if you are programmatically telling the oracle to mark the quantum state, then you already know the mark state. Then what are you looking for? But the point is of an oracle is that someone has been able to prepare the oracle. It is not me, and that someone actually knows the mark state. See, that's kind of verifying. Even if it is not knowing the mark state, it's kind of verifying. Because when if you write a program to solve and say a graph problem, an NP hard graph problem, and you try a brute force approach, you try all to the power n solutions, there can be a function which should look into your solution and verify whether this is a valid solution or not. The oracle, you can think, is like that function which can validate, and if it is a correct solution, it does something, it applies a phase, something like that. So there is one question is, we are still talking about gates and quantum circuits. There isn't actually. Quantum is still in a very naive situation, and that's why we still need to talk of gates and quantum circuits. We are not in a situation where we can go to a much higher abstraction here, but there are efforts. So recently, if you see some certain things called Qiskit functions have been provided from IBM, and not only IBM, many other third parties are also providing their functions in the IBM platform. And the exact idea is like this, that say you are trying to solve a chemistry problem. You don't need to go down to gates or quantum circuits. You give the inputs of your problem. It is like a black box that will do all these things on your behalf. So these efforts are ongoing, but we are still at a situation where we cannot avoid saying things like gates or quantum circuits. Yeah. Can you tell some algorithms that are specific to QML? Again, I am not really a QML expert, so um, perhaps not the right person. Whenever you have someone else talking specifically of QML, I would recommend you ask them. They should be able to give you a more proper answer to this. Yeah, thanks for all these questions. I mean, glad that you are interested in everything.
Thank you so much, sir, for this wonderful session on Grover's algorithm. I hope participants understood the fundamental of this algorithm. Thank you so much, sir. And regarding the quiz, we are scheduling the quiz at 6 p.m. So we will schedule at 6 p.m. and the deadline will be tomorrow, 11:59 p.m.
Thank you.
Thank you so much.
Thank you.
Thank you, sir. Thank you so much. Once again, quiz will be scheduled at 6 p.m. and you will have time till 11:59 p.m. tomorrow. So I have already announced in the group as well, WhatsApp group. The syllabus will be from the topics from July 17th to the topic till July 23. That is yesterday, excluding today's session. So today's session will be there in the third quiz. So any more questions regarding the quiz? Okay, I have also posted in the group as well. So again, whenever it will schedule, I will drop a message in the WhatsApp group. Okay, thank you.